Okay, good afternoon, everybody. Welcome to this, which is the first of the Johannesburg branch virtual meetings for 2022. I wish everyone a very happy new year, best for 2022, although I guess it's a little bit late to still be saying that, but as this is our first meeting, I guess it's probably appropriate. I see we have 37 odd delegates, which is a fantastic turnout, which is a testament to the currency of the topic which is going to be discussed tonight. I see some very old friends and some very familiar names in the ever-expanding list here. So welcome to one and all. I hope it's going to be useful. I'm certainly very interested to hear what Nicolas has to say. In terms of the topic, it is, as I've said, highly topical. With the publication late last year of the draft of the Global Industry Standard on Tailings Management, is a very high profile and a very keen view from investors, from shareholders, and various other stakeholders on tailings dams, and not just in their design and construction, but in their operation and then subsequent decommissioning and post-closure management. So hopefully Nicolas is going to talk to us about all of those things. Nicolas himself is a return guest. He spoke to us last year on satellite observation and measurement of various mining areas via satellites. He's a PhD in geology from the University of Pretoria. He's been a member of the SAMREC-SAMVAL working group for some time, so very familiar with a lot of the issues with which we deal. He's wide-ranging industry experience, geological, mineralogical, geotechnical investigations, and until recently was busy in remote sensing applications when he last spoke to us. Over the course of his career, he's worked on a number of tailings storage facilities, both locally and up in Africa. And we bow to his experience and wisdom and look forward to him sharing it with us. So Nicolas, without further ado, over to you. If I can just ask any questions, please post in the Q&A and we'll address those at the end of the presentation. Okay, we've got your screen, Nicolas. Just need to come off mute, I think. Great, are you there, Nicolas?
Yes, I'm here. Okay, thanks.
Awesome, thanks a lot. I'm going to switch my screen off and leave you to it. Thank you.
Okay, thanks for that introduction, Russell. So I'd like to say a very topical issue right now, and then we also had some of the guidelines that was coincidentally published this week in terms of the good practices. So thanks again for the South African Institute of Mining and Metallurgy for allowing me this podium to talk to you about the storage facility monitoring. So I'll be basically looking at a very broad view going forward. The topic is a bit aimed at your novice and people basically just interested in the topic itself. And we won't be diving into too much technical detail, although there are some technical aspects that will be touched upon. But generally, I hope that you find the presentation very informative. So where did all of this come from? So the need for tailings monitoring. So you've all have the background now of Brumadinho in Brazil. That was basically the main catalyst for requiring the reporting of all of your tailings storage facilities safety and hazard classifications. After that incident, the major investor, which was the Church of England Pension Fund, led the call for action to be taken globally for tailings to be reported on better and for the actual safety hazards to be reduced for all of the affected communities surrounding it. We then have the International Council of Mining and Metals, who were tasked to develop an international standard for tailings storage facilities. And the major mining companies all took the initiative after being requested so to start issuing a voluntary public reports on the safety of their tailings storage facilities. And in parallel, there was also an effort undertaken to develop a database of tailings storage facilities worldwide, which would then be available to view.
Nicholas, sorry to interrupt you. I have a feeling that your screen is frozen. We're sitting with just your front page slide and your resume slideshow text box up. Okay, I can see your mouse moving. Okay, there we go. Great stuff.
Okay, so
terrific. Thank you. Sorry about that.
Yeah, no, thanks for pointing that out. Okay, right, so that was in the basic background. Then a whole number of initiatives that were undertaken to actually provide the guidance initially, which would then crystallize later into specific legislation and professional codes that need to be adhered to. So on the South African side, the South African Institute of Mining and Metallurgy formed their task group to work on it, and there has been significant work done by them, especially in defining the specific roles and qualifications of the persons carrying the legal liabilities. And then, of course, this week, the International Council on Mining and Metals published their training material, which is based on the ICMM training management for your good practice guide during this week, actually, so good timing. So when we are now looking at legal liability, we have to look at your construction through operation phase, which is basically then your engineer of record, and that has to be maintained by him and carry the responsibility for the full lifetime of your tailings storage facility while in use. Then in the post-closure, specifically looking at the South African context here, for this presentation, the last operator is then responsible for the tailings storage facility, in theory in perpetuity, to ensure that the site is actually maintained post-closure. The only difference then is if there is a transfer of a mineral or mining right. For example, if you have processing of your tailings materials, and then that liability is transferred to the new owner of your tailings storage facility. So here you have seen this. You've seen this diagram a couple of times in the past. So this one is now specifically taken from the Anglo-American site, which then shows your different spheres of responsibility when looking at your tailings facility. So it will start off with your operations. So that is all of your routine inspections by the field staff. So the guys checking on the pumping of your tailings each and every day. That is the guys who also is quickly able to visually identify any potential risks that is developing on the tailings storage facility itself, and as well as then the engineer of record. So you can either have an on-site engineer, or you can have an engineer rotating between operations within a specific organization, or an externally appointed engineer as a consultant, which then do the quarterly and annual inspections. And then you've got your routine site inspection, governance, audits, and supports, which is done externally along with all of your independent reviews. Then internally, your technical assurance, which has an overview of all of your critical controls and your internal risk assurances that's being done. And then finally, your group technical specialists, which looks over your project and operational reviews for all of your best practice and risk management support, which is dynamically updated as new legislation is becoming more available, and then to keep it in line and reporting specifically to the specific code which is enforced in your area of legislation or your region. So in terms of self-reporting at the moment, there was a number of questions that was issued to your mining companies, for which they generally provide a summary table. So in your general information, they provide your tailings facility along with a name and identifier, along with a location, which is usually the center of the tailings storage facility, expressed in a universally accepted format, for example, WGS84. So it can also be tracked in the global database, and then indicating the ownership, i.e. the responsibility of the tailings storage facility, whether or not that tailings storage facility is owner-operated or contractor-operated. Then it gives you an indication of the status of the various tailings storage facilities within a specific mining cluster, For example, you have your active tailings storage facilities, which is actively being deposited on, your closed tailings storage facility, which reached their maximum rise of rate, and then all of your care and maintenance facilities, as well as then your abandoned ones, which is now falling under specifically the government in terms of care and maintenance on that side, and then an indication of your date of initial operation. So then in terms of your hazard identification, the general questions that came up is the dam currently operated or closed as per the current approved design? The raising method, so we'll just look shortly a bit later at the different raising methods of the embankments. The current maximum height, that's speaking to your maximum rate of rise as well per annum, and then the current storage impoundment volume, as well as the projected impoundment volume within the next 5 years' time, and then whether or not you have a recent independent expert review, so in other words, a third-party review of your documentation and reports that is available for public overview and scrutiny. When you have your due diligence type questions is, do you have full and complete relevant engineering records, including design, construction, operation, maintenance, and or closure, depending on the status of your specific TSF site? Then what is your hazard categorization of this facility based on the consequence of failure, and what guideline do you follow for the classification system? So that, for example, in South Africa, that will be SANS, and then you've got your various other districts. For example, you've got specific guidelines and classifications in Australia. In Africa, you've got, for example, in Ghana, and in South America, you've got a classification system as well, and other regions in the global setting is also developing specific classification systems for the development and construction of their tailings storage facilities. So then looking at the engineer itself who takes responsibility for the site, the questions are, has this facility at any point in history failed to be confirmed or certified as stable or experienced notable stability concerns as identified by an independent engineer, even if later certified as stable by the same or a different firm? And then do you have an internal in-house engineering specialist oversight of this facility, or do you have external engineering support for this purpose? All of this always plays into the risk rating at the end of the day. Then finally, you've got some of your ESG related questions. So that has a formal analysis of the downstream impact on communities, ecosystems, and critical infrastructure in the event of catastrophic failure being undertaken, and to reflect final conditions, if so, when did this assessment take place? So that will be looking at something like your tailings spill path based on your specific volume of your tailings dam within your specific topography based on an elevation model, along with the physical characteristics of the tailings itself, which might affect both formal and informal settlements in the downstream area. And then as well as any seepage that you might have, for example, acid mine drainage, which might also affect your ecosystems surrounding your area. Then once you get into your final stages of tailings before closure, it's a question again of if you have a closure plan in place for this dam and if it includes long-term monitoring. And then the final question is, have you or do you plan to assess your tailings facility against the impact or more regular extreme weather events as a result of climate change? For example, over the next 2 years, this is now especially been relevant in 2021, 2022, when the southern hemisphere had a La Nina weather conditions that were dominating over the area. And we heard from a couple of operations, especially in Latin America, Brazil, Chile, and Peru, where operations had to be ceased and suspended for a number of days due to excessive rainfall within that area. And we also had another small collapse of the tailings facility, where you had runoff from a road, which actually then led to overtopping of the tailings storage facility. So then to give us a very brief overview of the types of tailings storage facilities that you get. So first off, to start, what is a tailings? What is tailings? So tailings are the materials left over following the processing of mined ore that separates valuable metals or minerals from the host rock. So tailings are not the same as waste rock, the latter being soil or rock or other material that covers or surrounds an ore body and that is displaced during mining, but which is not processed. So then if we look at fines itself, tailing fines, you'll see it generally comes along with a range of analysis. So the main analysis is your particle size distribution. So that gives you, number one, an indication of the effectiveness of grinding at your plant, and then which is shown on the left-hand side, and then on the right-hand side, you have a view of tailings under a microscope. So the dark gray material are the silicates, and then the grayish to yellowish minerals are all of your sulfides that was recovered from your tailings as well. And all this information is then fed back also in terms of the effectiveness of your plant, and the potential then eventually of potentially reprocessing some of your tailings. So as you would imagine, the size of your tailings will have an effect on the rate of settlement. So it will have different depositional conditions and stability based on that, based on the angularity of your tailings, as well as your environmental or climatic conditions. For example, an arid region versus a more tropical region in terms of both settlement and potential overweighting of your tailings material as water is being seeping through your unconsolidated material down to the level of seepage direction. So then to just give you a very high level overview of what a tailings storage facility looks like. So we've got different ones, but in principle, most of them remain the same. So you generally start off at the bottom with a textile, which protects the groundwater and the phreatic zone from ingress of tailings-derived water and acid mine drainage into your water table. Then you've got your starter dikes on either side, which is then built up to contain your initial deposition of material. So your slurry discharge will then always start from your starter dike, and that will be used to build your different lifts. You've got your coarser grained material, which goes through your cyclone and is used to actually build your tailings wall, and then the slurry is flowing down to the lower slope angle of the tailings containment area, with the pond water being ponded on top of that, where you've got then the interaction with the atmosphere itself, leading both to evaporation of your pond water that is then reducing the total surface area being affected, but then also being affected by rainwater in terms of precipitation, which might then fill up your pond area again, affecting the amount of freeboard that you've got. So you will always have a preferential deposition from your discharge location to your pond area discharge settlement area in terms of the grain sizes as well, which has a bearing on that. And then we'll look at the other elements a bit further now. So again, using the Anglo-American standard description for the different types of tailings storage facilities which are constructed. So the number one, which is in terms of hazards, is your upstream construction type, and the upstream has now actually been completely banned by Brazil, and they have set a target to actually remove or recondition all upstream tailings storage facilities within Brazil within the next couple of years. The initial date being set 2022, but then realizing it was a bit overambitious. So the upstream method basically starts with the construction of a starter dam. The tailings will be naturally separate so that coarse material settles closest to the starter dam, while your liquid and fine material settle further away. As the level of the material rises, the crest of the dam is raised upstream side, using the support of the previous dam raise and the tailings breach material. So as you can see from that image, each one of these is actually only partially supported by the previous construction and further resting on tailings slurry material underneath it. Then you've got your downstream method. So this is a slightly better method, with the downside that your footprint area for your tailings storage facility actually increases over time. So it begins in most cases with a starter dam again, like most of your tailings facilities, that has a low permeability zone or liner to control and minimize water loss. In some cases, it also serves to initially store the water for startup of the plant. So all your tailings is then again placed behind the dam, and the embankment is raised by building the new wall on top of the downstream slope of the previous section. Then we go to the centerline one, which is basically stacking on top of one another. So the centerline method sits between the upstream and downstream construction method. Much like the upstream method, the tailings are discharged on top of the dam to form a beach behind the dam wall. When the dam is raised, the material is then placed on both the tailings beach and the existing embankment material. Then you've got a hybrid, so this is envisaged for especially a lot of your sites now in Brazil, where a hybrid dam is then a combination of different types of previously defined dam types, including downstream, upstream, or centerline, and that changes construction type in the past and is now being defined as a hybrid type. Then you've got your landforms. So this is very historic type tailings. So the example I'm showing you here is from the Barberton area. So this is basically a legacy tailings dam that has dried out to the point where it does not constitute a wet dam anymore and is not considered a dam or containment structure at all. So the main features are the outer wall slopes, which may be altered or flattened by erosion to a point that the facility is unrecognizable in comparison to its previously engineered state. And as you can see here in the example from Barberton, a small village has actually been built on top of that tailings storage facility itself. Then the final one is your water retaining type. So that's in the left-hand side of the image. We have water being retained by a dam that is built by using selected imported fill material from designated borrow areas and quarries, or in this case from the open pit itself, and then placed in a controlled manner in the lifts, typically resulting then in an embankment structure that is designed to store water and tailings in direct contact with one another. The water retaining feed structures may have been specifically engineered to have specific structural features, for example, riprap, a low permeability liner, or a core zone, internal fillers, and a drainage system to safely manage stored water and seepage flow through the dam body itself. And in a lot of cases, it is built in such a way that it actually capitalizes on the topography of the setting in which it has been placed. So then we will now look at your different failure modes that you get. So as you'll see from Grilla, I did a quick summary of the main causes of tailing dam failures between 1915 and 2016. So that's looking at a 100-year record. You'll see that overtopping, 44 of them, has been the leading cause, where it's been overflowing. And then slope instability, we have static failure, is also then induced by oversaturation of your dam, and then 17 of these are again due to seepage and internal erosion. And so as you see, water is the main culprit in any of these type of settings in terms of failure, which is part of the construction process and management process. Then the one that you do not really have control over, 27 of them being earthquakes, i.e. seismic instability dams. So that actually requires then extra engineering to be performed on the dam itself. Then when we look at seepage now as the main culprit, you've got different types, which is briefly summarized in this graph. So you've got your high water levels due to inadequate drainage facility, mud flows in the event then of a dam failure. And then you've got number 2, which is your inherent size segregation and layering, producing a deposit with different hydromechanical properties in the vertical and horizontal direction. So again, as I pointed out earlier, when we look at the particle size distribution as well as the actual coarseness and angularity of your tailings being deposited. And then number 3 is early sedimentation results in loose sediment structure, which may collapse during loading in the event of a seismic trigger or dam failure. So this is something that happens in terms of a liquefaction event then of your tailings, which was previously considered stable, but then due to seismic induced activity liquefied again, especially in the presence of water. Then you've got your heavy rains, which causes overtopping, again, like I mentioned earlier, specifically in Brazil, where you had extreme weather conditions in terms of excessive rain. And then number 5, you've got your compressible and low permeability fines close to the embankment that reduce your dam stability. Then number 6 is the final one inside, so that is slip along pre-existing weak seams in the foundation, which can lead to global shear failure. This mechanism is aggravated by rapid increases in dam elevation. And then the final one is looking at the infrastructure along the wall itself, so that's all your internal piping erosion, fines migration and mineral precipitation progressively change as your fluid pressure distribution and can compromise your dam stability. So this is especially important for the guys doing your daily slurry pumping checks to watch that you actually do not have compromised infrastructure. So then we also have over time a change tolerance that you do look at. So other than failure changes, you've got settling of tailings over time and drying, which you need to account for. And then once you've got your final or maximum rise of rate and you have closure of your tailings facility, you then need to remain cognizant of erosion over time, especially in the case when where you have ineffective stabilization of your tailings walls. So how do we do all of this monitoring? So it starts off when on site doing manual monitoring. So it's a geotechnical engineer or a geologist in combination then with your plant engineer and your mining engineer along with your management to take responsibility that you need to report to, that report on specific site investigation results. So we start off with a visual inspection and measurements from stationary instruments as well. Then identifying of potential indicators of failure. The downside of that is usually because it is not a designated task, you sometimes have a rotational engineer or a contractor and the end comes out during a specifically predefined frequency, for example, quarterly or annually. There is a bit of high cost in having such a person, and then a lack of continuity, especially over a long period of time. If you've got different persons working on it, that reports findings in different manner. As well as when some of your historic material which is not consistently logged. Then you've got your instrument monitoring, so that gives you a more consistent review of specific elements within your tailings storage facility, which is then reported on. So that relates to pond elevation, the piezometric pressures at your phreatic zone, installed clinometers, and then finally all of your meteorological data, for example, a small meteorological station installed next to the tailings storage facility to just keep tabs on what is going on there. Then you've got your installed fiber optic cables, which is then able to detect sub-millimeter movement, along with seismic monitoring, which is a passive method that is used. And then you've got your central surveillance centers, which all of the information is collated to. So let's start at the start. So when the geotechnical engineer arrives on site, he usually does a walkabout around the tailings storage facility, looking at specific sites of the tailings storage facility, usually critical areas which has predefined risks associated with it. So all of that is then captured into a photo database. So we've got a photo record in terms of that development and closure of your dam over time. So when you've got your clipboard, or nowadays you've got your surface with specific entries that you do for your area. So walking along the crest or inspecting the crest, you note the current elevation and then the reservoir level or the remaining freeboard that is measured on top. Then distance to the tailings pond. Then looking for any surface cracking. So the surface cracking is specifically related then to subsidence of the tailings storage facility wall itself and not just desiccation cracking. Looking for any unexpected settlements that would usually be expressed in terms of something like a little sinkhole, anywhere where you can note a lateral movement or any other unusual conditions that you might pick up while doing the inspection. Then you look at your upstream slope where you record your slope angle, any signs of erosion, signs of deformation, again, further cracks which might be related to your deformation or settlement, again, not just desiccation cracking, and then your face liner condition along then with any other unusual conditions which you might observe. Then you go down to your downstream slope side, and again you note your slope angle along with any possible erosion, movement, cracks, seepage or wet areas now, because this is where your ponding of water takes place. Then vegetation growth, which may serve as a proxy for seepage which is not visible, along with any other unusual conditions which might be noted. Then you can look at your downstream tow areas. So there you look again for seepage from the dam itself, along with erosion. So when you look at the seepage itself, and you can see actual turbidity, so in other words, you can see physical flow in that seepage, that needs to be then marked as a high priority. Along with discoloration, so you've got migration of elements, which then basically, when it again makes contact with the atmosphere, oxidizes and results in discoloration on the side of your tailings storage facility. And then outlet operation problems which might be noted and then reported to the relevant engineer, along with any other notes. Then shortly you will go to the abandonment area, where you will note your seepage at the contact zone itself. Again, any possible erosion that you might have, excessive vegetation, again, excessive vegetation being a proxy for seepage which is not visible, and then rodent burrows. So this is actually more related to your infrastructure. So you've got things like porcupines and so on, which can either smell or hear flow in pipes, and then basically claw and gnaw at the pipes itself, along with any other types of anomalous material which you can note. Then finally, just looking at your reservoir area, you again look at the stability of your slope around the reservoir, and then noting any floating debris which might be present in the reservoir itself. So then you move on to your installed instrumentation, which then gives you your long-term readouts. So we start off with prisms that's usually installed along the crest of your tailings storage facility. The type of results which are presented to you over a timeline is then your vertical displacement and your horizontal displacement, and then also a calculated cumulative relative displacement, which you then use to interpret your displacement, and then finally an average velocity, which can also be reported on. The GPS unit is usually installed at key points along your tailings storage facility and not just along the crest. Again, it gives you the same type of output which you look for, which is your vertical displacement and horizontal displacement, and then your calculated cumulative relative displacement graphs, which you use for interpretation. Then you've got your installed inclinometer, so you basically have a drilled cased hole where your inclinometer is then anchored in your bedrock, and then it measures the changes in incline over specific height intervals. So expressed in this case as an A-axis or a B-axis movement at specific depths. And then finally, you've got your vibrating wire piezometer, so that measures then the water level at your phreatic zone, again over time, which you then use for your annual inspection reporting periods. Then other potential methods that's being used for passive monitoring. So a lot of these are still in proof of concept phases. So you've got your passive seismic, so that uses ambient noise to image the interior of the tailings dam. This technique identifies the phreatic surface levels within the dam and is then used to identify any potential soft or unconsolidated zones. Then you also have your fiber optic sensing, so you have that installed in the tailings dam itself, and that then provides you with near real-time monitoring of strain, deformation, and seepage. A lot of these fiber optic sensing systems is linked to a satellite communication network, which then allows the data to be almost communicated in near real time to a central monitoring position or central monitoring station, where alerts can then be generated in terms of potential catastrophic failure of tailings storage facilities. So in the last couple of years, drones have become more and more popular to do all of your tailings surveys along with your normal site investigations. So it has a couple of advantages. So it allows you to now actually access the dangerous sites with minimal risk to the staff in the area, which might previously not been able to investigate. The cameras that are mounted on the drones give you fairly high resolution imagery, and you have the capability of being flexible in terms of a multitude of sensors that can be mounted on your drone. Drones can also be used in almost any type of weather condition, and it's not barred by something, for example, like overcast weather, but is limited in terms when you've got heavy winds and heavy rains. And then the biggest upside has been the low operation cost. There is, however, a couple of limitations. So for operators needed to be licensed in order to operate drones on site, and depending on your jurisdiction where the tailings storage facility is located, you have either flight restriction on drones, or you need authorization to be obtained prior to undertaking any of your drone-based surveys. So the main applications for your drones are when monitoring and surveillance of tailings storage facility and related infrastructure using the high-resolution photography and video photography that can be replayed after the drone has landed, and then it can be used to do wet spot detection using thermal imagery. So tailings water will always be slightly hotter than your ambient environment or any of your other groundwater sources. Then it allows you to do remote water sampling along with in situ analysis, and then you can do surveying, data processing, and interpretation of that data, which is then fed to your survey department. And it also then allows you to do volume calculations in terms of reporting, or if you have potential reprocessing that you want to do. Then a couple of companies have been developing dashboards. So that's usually a web-based application. So your site staff will have a smartphone or a tablet in which they use then to do entries at specific points. That is then either fed directly if they've got a Wi-Fi connection to the system, or it can be stored temporarily on the device itself and then downloaded as a burst download once they have connectivity again. All of that information is then sent to a central processing site where the data is captured and ingested to produce a uniform data display, and then to produce all of your value-added products, allowing someone like your legally responsible person along with your mine management to then have all of the results at their fingertips in case they need to make a quick decision. So then moving up a bit further in the sky, we've got our Airborne Survey. So that's usually with airplanes that fly over, and they can do either a LiDAR survey of the area, which produces a point cloud map like shown on the left-hand side, or they can do conventional stereo photography, which is then used through photogrammetry to actually produce your volume products calculations. And then when we leave Earth's atmosphere, we've got a couple of satellite platforms that you can also use to monitor your tailings storage facility. So you have the option of two types of platforms that you can use. The first one is your public domain satellite imagery, which is made available through government organizations. The upside is that it's usually free to obtain within a couple of hours of being made available. The downside is it's got a fairly low resolution, and you cannot specify your area of interest, which means you might not get your full tailings storage site within a single pass, and then you might need to do mosaicing and all of the related downside that actually goes with not getting it in a single pass. Which relates into your long repeat pass intervals. So it takes a couple of weeks sometimes before a public domain satellite passes over the same area again, and you get both optical and synthetic aperture radar data, which is made available online. When you've got your commercial suppliers, so the downside here is it's fairly a high cost to task a satellite to actually do an acquisition over your area of interest. The upside is that it is usually very high resolution that you do get from it, and you are able to specify your area of interest, so you get the entire area in a single pass potentially. And then you can program it for a specific date of acquisition, so that might fall then in line with what you are doing in terms of your surveying mark updates. Some of these suppliers also do pre-processing before the imaging is supplied to you, and then you are able to instantly either get from them or generate value-add products for your tailings storage facility. So looking at your optical side, you've got your electro-optical, so you've got a range of visual bands, so that's red, green, blue, and near-infrared, and then hyperspectral bands, for example, SWIR, which is made available to you. Depending on the different bands you've got in your optical image itself, it will determine the type of outputs that you can generate later as a value-add product. So for tailings storage facility, it's better to actually have a high-resolution image. So right now, commercial platforms are offering 50 centimeter and 30 centimeter resolution optical images. You will usually acquire a mono image if you are only interested in doing change monitoring, for example, vegetation changes or surface water changes over time. And then you need to do stereo imaging if you want to do volume product calculations or generate a terrain model. There are a couple of limitations with these platforms. You are limited to doing daytime acquisitions, and a lot of this is affected by cloud coverage itself. So the main applications for optical imagery is then pond management. So you've got your surface water area that can be detected, but not water depth. You can do monitoring of your tailings beach width, for example, then to prevent an overtopping event by redlining it. And then looking at your post-event monitoring, for example, if an overtopping event or spill event occurred, then you can actually do monitoring of the area while you're still waiting for other services to be able to access the area itself. And then over the long term, you can do weathering and erosion impact tracking of your tailings storage facility. Then the other one, which is very important, is your volume product. So it can calculate both volume as well as volume changes. You can then use it to track as-built volume during construction until you reach the maximum rate of rise. And then you can supplement all of your scheduled inspections. So in between your quarterly or annual or semi-annual inspections, you can still obtain imagery, which you can then scrutinize in terms of potential changes on site. And then if you've got a volume product, you can also do a high-level remaining freeboard calculation. So basically an output would look something like this. On the left-hand side, you have a volume product where you can then see over time a change in the height of the wall itself, and then you can use it to do a high-level calculation of the wedge, which will give you an indication of the remaining freeboard. And on the right-hand side, you can see the red-lined area where you've got your tailings beach potential for overtopping that would trigger an alert. And you have the potential to also indicate areas where you have between acquisitional timestamps an increase or a decrease in surface area water that is being detected. Then we move over to synthetic aperture radar. So that's basically where you can now start using interferometry. So that uses phase differences between acquisitions to detect surface deformation on your tailings storage facility. The advantage is that this data can be collected both day and night and is not affected by cloud cover. It is especially used then in the equator areas or any other of your areas where you have potentially persistent cloud cover. There is, however, a limitation in terms of the application over very active tailings storage facility sites due to very dynamic changes. And then, of course, if you've got very large surface water areas which cover the top of your tailings storage facility, or if you've got very dense vegetation in proximity to your tailings storage facility. And again, you've got a fairly low repeat pass interval, anywhere between 11 and 12 days, which limits your potential to actually do real-time monitoring with satellites at this moment for any of your tailings storage facility. So the main application here is surface movement monitoring, or SMM as it's more commonly referred to. So you are able to do detection of vertical movement, i.e. subsidence of around 2 millimeters to 5 millimeters. Then depending on the constellation you are using, you can have only a single line of sight observation over your area, or you can have an ascending and descending pass over your area of interest. If you only have line of sight, then you will still be able to do a vertical movement interpretation. And if you have both ascending and descending passes, not only will you then be able to do a vertical movement delineation, but also infer horizontal movement. But you do again have the limitation where you potentially have obscured sides depending on the orientation of your tailings storage facility. And then in terms of, like we indicated earlier, water being the main culprit in some of your failures. So you want to look at water ponding as well as wetting of your tailings. So that's usually using SARDC with a company in Cape Town, having done fairly groundbreaking work in using that approach in terms then of generating potential alerts of failure. Then when we look at the different outputs that you do get from INSAR type monitoring, you can do either point monitoring, a long line monitoring, or a specific area of monitoring. The outputs usually are then velocity and displacement. So most common industry method then of using this output to delineate the potential of a failure and to generate an alert is using your inverse velocity graph. So that's expressing then the days per millimeter over days. So you can see from the graph itself, you've got your pre-failure behavior there, and then you've got an inflection point. Then by extrapolating that data points until you reach the 0, you can then indicate a potential date of failure or amount of time until failure, which might allow you sufficient time to put remedial measures or catastrophic prevention or evacuation measures in place for communities affected by potential spoilage. Then you also have your persistent scatter interferometry or PSI points. So that is points which are expressed along the walls of your tailings storage facility. Then using your displacement intervals, so your mine will usually indicate to you a specific subsidence which is within their tolerance levels, which they expect it to actually be annually. And then you've got different category intervals in terms of risk for potential failure of a subsidence risk which exceeds that tolerance level. In this specific case, then all of your green points are points that have remained fairly stable between acquisitions. And then as your colors become hotter, moving from yellow, orange, red to red, it then gives you the ability to delineate a specific point where you might have a potential failure event. So basically moving then into the last section of what we are presenting is, so what are the different phases that you do your monitoring in, and what do you do during those phases? So site planning and preparation. So that's using your digital elevation model or your DSM or DTM that you obtain. So that is used then for the placement of the tailings storage facility along with all of the associated infrastructure, modeling of the topography for designs of your retaining walls. It can also then be used in terms of your regional hydrogeology studies. It can be used in terms of your spill path prediction that you can set up, and then any potential settlement detection within that area that will be affected by it. So this is basically what a digital elevation model will look like, and it will define to you specific areas where you will have the flow path of potential spillages along with potential development in terms of regional hydrogeology. When during this construction phase, all of the monitoring is usually done during the survey and project management departments. So you will be looking at your volume product, so that is your monthly quality assurance, and your check as built surveys that's being performed. And when you do all of your GIS integration, so that would be tracking the progress to milestone dates, monitoring dam and water reclaim facilities, and then to evaluate the conformance to the design line and or grade of your dam as it's being constructed. During the operational phase, your main monitoring activity relates to your minimum freeboard elevation and then the conformance to your operational requirements. Then you will also do evaluations of your tailings beach length along with your cyclone zone paddock construction. And then it allows you to do a number of estimations relating to your construction volumes and rates, your projection of remaining capacity or each rise, and then your in-place density or deposited tailings, and then forecasting future construction activities based on all of these inputs. So this thing just gives you a quick idea of what a tailings storage facility looks like while being in operation and having slurry pumped in. So this is the top left-hand corner where you have your slurry deposition, and then you can see how it flows down to your pond area in the bottom right hand. Then an important function, as mentioned a bit earlier, is your pond management, where you have both plant-derived tailings and meteorologically derived precipitation water, which then ponds in your tailings storage facility. It's one of your main safety considerations, especially for overtopping, and then it also gives you a proxy in terms of an effectiveness indicator of reclaiming water by your plant. Then by redlining your tailings beach area, it gives you a warning if the aerial extent of certain parameters are exceeded in terms then of your surface water area, and then triggers an alert for overtopping. Then, after you've reached the end of life, the final race of ride, you've got your post-closure phase. So now you are basically going into security mode. You're looking at infrastripping or vandalism going on around your tailings storage facility, as well as keeping tabs on any illegal mining or reprocessing that's taking place on site. Then you also have to ensure that you do continued failure forecasting, so looking at the effect of erosion as well as water accumulation on top of the tailings storage facility, and then also still looking at potential movement or subsidence of your tailings storage facility, like you can see in the image there, where it's located next to a residential area. And then finally, your rehabilitation that you look at, for example, the success of vegetation re-establishment. So planting of, in this case, black wattles to help stabilize the walls itself and the top of the tailings storage facility, and then to keep tabs on other environmental processes that could also negatively affect it. For example, potential acid mine drainage. There you can again use your drains to do thermal imaging and use, for example, SAR-DC to delineate your overweighting of tailings material, and then finally you can use some of your either visual, your NDVIs as a proxy when you've got your optical visual bands to determine where you've got dying of plant material, which might then indicate potential acid mine drainage within your area. Okay, then I would like to thank you for the time you gave me, and thanks to Russell and Kia for making this platform available to me.
Wow, Nicholas, that's a lot of information. Thank you. That was absolutely fascinating. There's a couple of questions so far in the Q&A boxes, but before we go to those, perhaps I'll just pick up on something that you in your penultimate slide, or the one before, you said about planting black wattles to stabilize dams. Surely those are invasive aliens, and the environmentalists are trying to get rid of them, not put them in, not plant more of them.
Yeah, no, I was just referring to a specific image there, but yeah, you are correct. So, yeah, depending on the region you are, so in Australia and so on, they can use black wattles. You've had invasive black wattles, so especially if you drive along the N1, you'll see some of those old tailings. There's a lot of black wattles on those, but yeah, you are correct, that is actually an invasive species. But yeah, until we find a specific grass or an indigenous shrub, yeah, they'll stay there.
Are they particularly good at binding because of their water take up and that sort of thing?
Well, basically they are fairly resilient plants, it would appear from what I've read, so they can actually withstand toxins within the tailings storage facility, and like you say, a lot of these Australian plants, the black wattle and the blue gums, actually do absorb a lot of water as well.
Okay, thank you for that. Okay, the couple of questions we've got so far. How does the standard make allowance, and I assume this is the GISTM or the more recently published one, how does the standard make allowance, if at all, for South African weather conditions as opposed to those experienced in Brazil? All reference failures, so you mentioned, were in Brazil.
Yeah, okay. I will have to review if there's something specific in terms of climatic zones, but yeah, if we just look at the comparison between South Africa and Brazil, South Africa is a fairly semi-arid region, so we've got some extreme weather conditions here, but yeah, so you've got isolated events. In terms of rain that happens, especially now with La Nina, even it's not continuous. But if you are looking at, for example, Brazil, the Minas province, where it's actually a tropical setting, so you've got continuous higher humidity and so on. So if you've got then a slower drying of your tailings storage facility, and then if you've got persistent rains like this, then you actually have lower evaporation, lower permeability remaining in the tailings, so that then leads to a more frequent occurrence of overtopping.
So if I'm understanding you correctly, Brazil is a worst case environment compared to our semi-arid South African conditions.
Yeah, so it's just basically comparing your climatic conditions. So yeah, like you say, South Africa is semi-arid, whereas the affected areas in Brazil has so far been tropical.
Thank you, Ian. I hope that answered your question. Then one from Teboho. Excessive vegetation growth is monitored where? I.e., is it at the toe of the dam or in the paddocks when you refer to the measurements?
Yeah, so that is basically, no, you have to, okay, so this is up to the observer itself. So you usually look at the downstream areas along the toe, and then you basically look at your environment, if it's excessive relative to your environment itself, or if you've got higher growth, denser growth happening along that, or if it's clustered. So it's a bit subjective to the viewer itself. Okay, thank you, Teboho. I hope that answered that one. And then finally, a comment from Peter Radcliffe. Have you published, or are you considering publishing this paper in the SAIMM journal, which will be of great value to all operators? Yeah, so there was one published in the so there was, following the 2020 tailings, there was one published in SAIMM for satellite observations. Then there was another one that was published as part of the abstract volume for the 2021. And then this paper is now a in progress one. So it's still being circulated by my own internal reviewers. Okay, thank you. Okay, Ian's come back. He's followed up on the climatic conditions. His question is more that we're being held to a standard which is not applicable to us. How does the standard allow for difference in weather conditions? We seem to be being held to a standard designed for tropical conditions. Yeah, I think I think to some extent this is something that still needs to be hashed out as you go from guideline to legislation. So obviously, the more input from industry you get pointing out site specifics, which is basically then considered hazardous, but then you've got to make all of your cravat type statements. I'll be honest with you, I haven't really looked at weather conditions in terms of the guidelines and standards, so I'll just have to read to that and probably get back to you. But you've got my email, so send me a message, and then I'll have to look into that. No problem at all. Thank you, Ian. So just drop me an email, and then I can either connect you with Nicolas direct, or we can run it through me. It's quite an interesting topic. I'm interested myself. So thank you for that. Okay, another question. How widely is Inmarsat tailings monitoring in use compared to INSAR? I'm not really going to do marketing for anyone here. Are those commercial brands? Yeah, Inmarsat is a commercial brand. Okay, fair enough.
Okay, well, that's all the questions that we have come through. So, Nicholas, it just remains for me to say thank you again. That really was fascinating, very interesting, and a lot of information, a lot for us to absorb. The presentation will be uploaded to YouTube and accessible via the Institute website once it's been saved and formatted and made a little smaller than it currently is. So anyone who wants to review it, it's available there. Nicholas, thanks again. To all our attendees, thank you. Really appreciate you taking the time. Hope you found it as interesting as I did, and look forward to seeing you again, hopefully at the next meeting in March.
Yeah, thank you very much for the opportunity, and thank you everyone for the participants.
Thanks very much, everyone. Thanks. Good evening.
Thanks. Goodbye.